This week at our Teichmüller seminar, we have the pleasure of hearing Richard Kent from the University of Wisconsin-Madison, who's going to talk about spacious knots.
Yes, thank you very much. Thank you for the invitation. It's nice to be here. So I talk about spacious knots. So to be honest, the way this talk is sort of structured at the very end, I'll mention the spacious knots, but most of it is sort of motivation for the statement of the theorem, and so I won't talk too much about the technical details. But what I'd like to do is talk some about, most of the time, about a motivating problem that sort of isn't. So I'd like to talk about motivation, but it's based in trying to prove the virtual Haken conjecture, which we don't need to do anymore. But a lot of the motivation for the background for this problem I want to talk about comes from sort of an old approach to an old naive approach to virtual Haken. So let me mention the virtual Haken conjecture due to Waldhausen. Well, so what does it say? So it says, say, let M be a closed just doesn't really matter. So just a closed irreducible three-manifold with infinite fundamental group then M has a finite cover that is Haken. So Haken means that there is an embedded pi1 injective surface. That's not a two-sphere. Okay. So any embedded two-sphere is a embedded pi1 injected surface. So we don't want that. Okay. So that was the virtual Haken conjecture, and so this is now a theorem. So this is due to Ian Agel, but really, I mean, so the proof is sort of so hard that I sort of want to list some other sort of major players in the proof of the theorem. So it's Ian Agel's theorem that the virtual Haken conjecture is true, but you also need sort of a major piece of it is due to Donnie Wise, and then so I'm not sure commas and sort of plus signs and stuff and hyphens aren't sort of sufficient to tell the story. But so due to Agel and Wise, and then you also need important players here. So this is sort of Egel's theorem and sort of maybe say major input. So there's Kahn and Markovich. Okay. And then also, you notice here that this is just a topological statement. And so Egel's proof of this theorem actually uses geometrization to start. So you actually need Perelman. So I'll mention sort of at various points why you sort of need this, and then to get this. Okay, so this is now a big theorem, and so we don't need to necessarily worry about trying to establish this anymore. But what I'd like to do is motivation for talking about spacious knots is I'd like to talk about sort of before this theorem was proven. Let's go back and think about if we just try to approach this naively. And what I'd like to do is just mention the names in this theorem and the fact that the sort of the basic groundwork you begin with is Perelman. So you begin by assuming geometrization, and then you need that to get to this major theorem, and then you use this major stuff, and then this major stuff. So it's this huge apparatus that proves this theorem. So this is a very hard theorem. And so I'd like to maybe just sort of start out by just talking about how hard you might think it is, even before knowing about how hard the proof is. So let's assume we don't know it's a theorem, and let's just think about what will we do. And so let's think about some of the outputs of the hypotheses. So we just start out and we just have some closed three-manifold, and it has infinite fundamental group, and it's irreducible, sort of technical just thing. And we want to conclude that it has a finite cover that's Haken. Okay, so let's just so one thing the conjecture says. So one thing the conjecture asserts is that there is a finite cover. Okay. So that alone is hard. Okay. So if you just give me a triangulation of a three-manifold, and you say its fundamental group is infinite, I was told that, and where are you going to get a finite cover from this? So maybe. So the board will be covered with lots of hypotheticals for a while. So maybe M has no non-trivial finite covers. So M is a finite cover of itself, but that's not very interesting. So if you want a finite cover that's Haken, you'd better have some finite covers to begin with. Okay, so
are there examples of manifolds that don't?
You could just there are lots of groups that have no finite index subgroups. So there are infinite simple groups. So I guess we'd have to know that there's no, say, infinite simple three-manifold group or something. So I don't know. So I think even to prove this statement, so there are lots of four-manifolds, say, that have infinite fundamental group. That it's torsion-free and there's no finite cover. So even just proving this, I think we'd need Perelman to do this. Okay. Okay. Right. Okay. So what we'll do is, so this is hard.
So
Yeah.
I guess so this is in the case that M is not already Haken, then it says that there's a finite index cover, or is that, am I reading that correctly, or?
I mean, even if it were Haken,
Or is that
it's
automatic?
not obvious that you have a finite cover.
No, but I mean, does the theorem say that this is a finite non-trivial cover that's Haken, or?
Oh no, but I mean, okay, yeah. So everything could be Haken, but I guess there no explicit examples, I guess, of non-Haken manifolds.
I think you're asking if it's already if it already has a pi1 injective surface, but then the surface has a the fundamental group of the surface has a subgroup of finite indexes. No, I guess.
No. No.
That doesn't.
No, it's not related.
Yeah.
So yeah, okay. So yeah, I don't know.
Yeah, I was saying, I mean,
There's certainly zillions of non-Haken manifolds.
Yeah, I mean, I guess a priori the virtual Haken conjecture doesn't prove that there's a non-trivial finite cover,
But what?
Okay.
Yeah.
right?
because it could be Haken.
Because it could be Haken and just have no, and just still be simple, yeah. That doesn't happen, but that a priori, yeah, right.
So just to be clear, if you know the M is hyperbolic, then it's obvious it has finite covers.
That's right. So I'll pay you later. This I've never seen it before. So this is actually what I would say right now. So since that's already hard, we'll just assume this part away by assuming that M is hyperbolic. So if M, so we assume this away. So let's say we're just interested in proving any good case of the virtual Haken conjecture. And so we'll assume this issue away by assuming that M is hyperbolic. So okay. So in that case, the fundamental group sits inside of PSL2C, and which is linear, and so pi1 of M is actually residually finite. So, in other words, the intersection of all of its finite index subgroups is the trivial subgroup, which in other words means that for every element of pi1, there's a finite index h, say such that gamma is not in H. Okay? So if you have any finitely generated linear group, then it has this property. And the proof, that's, I guess, is that due to Malsev or so you essentially just can reduce modulo primes or something. Okay. Okay. Okay, so in this case, so assuming M is hyperbolic,
So that's a property of discrete subgroup of PSL2C?
any finitely generated subgroup of GLN.
I
See.
see. I see.
Yeah, so this is the P might make you worry or something, but PSL2C is linear by an accident. Assuming M is hyperbolic, pi1M has lots of finite index subgroups, and so M has lots of finite covers. Okay. 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 So I'll keep the virtual Haken conjecture for a little bit. Is that clock not running?
Instead.
Okay, that's okay.
I was giving a lecture at the same time.
It's correct more often than a running one. So. Okay, so right. Okay, so we'll just assume that the manifold is hyperbolic, so we have lots of finite index subgroups to work with. Okay, so now what else does this say? Well, it says it says, you know, find me a finite index subgroup or find me a finite cover. So we've done that. There are lots of them, and now it says not only that, find one that's Haken. Okay, so and that means we want to find an embedded pi1 injective surface. Okay. Well, there's two parts of the Haken, you know, the word Haken, and there's embedded and pi1 injective. So maybe we just forget about embeddedness and we just need to find a pi1 injective surface, period. So what about so another thing this says, that we can find a pi1 injective. Should maybe cut the board into smaller pieces. So find pi1 injective map S to M, okay, where S is a surface that, you know, isn't a two-sphere. Okay, so we can find some immersion of a surface into the three manifold that's pi1 injective. So notice here I haven't gone to the finite index subgroup or the finite cover, because actually if you have if I don't care about it being embedded, all I am asking for is some immersion, and then if I push down by the covering map, I would also have an immersion down into the original manifold. So a basic corollary of this would be that there is a pi1 injective map of a surface to the three manifold. Okay. Okay. So how do we do that? So maybe let me go back, and I'm going to write these names sort of in a little box on the board again. So Agel, Wise, Kahn Markovich, and Perelman. Okay. So Perelman in the actual proof of virtual Haken, Perelman allows us to assume that M is hyperbolic. So the virtual Haken conjecture in the non-hyperbolic case, you can sort of, handle, in some other way. And then, so that's sort of the Perelman input. And then, the actual proof of virtual Haken, the surface subgroup comes from this theorem of Kahn and Markovitch. So they actually produce, if you give me a closed hyperbolic 3 manifold, they give you a surface. So in the present day, Kahn, Markovitch do this. Okay.
Okay, so now I'm getting confused about who, what, when. So Kahn Markovitch doesn't need Perelman?
Yeah, so so how do we do that? So assuming, so we're still assuming hyperbolic, okay? So now Kahn and Markovitch need the hyperbolic input, and they will find you a surface subgroup. And sort of back, when Waldhausen, posited this conjecture, their proof of that theorem would seem completely alien. It heavily uses the hyperbolicity of the manifold. It's sort of dynamical in that it uses essentially uses the geodesic flow on the 3 manifold, and it's sort of statistical in that they sort of just construct lots of potential surfaces, and then it's sort of essentially probability tells you that there exists this surface embedded in the 3 manifold. So it's very sort of modern, just constructing this surface. But let's just still assume we're sort of just approaching this as if we only know 3 manifold topology, and this is what we're doing. So let me maybe mention how. So why is it again this is hard, and why might it be hard? Let's just maybe pause and think about what a weird manifold it would be if there were no surface subgroups at all. So imagine that you have some closed 3 manifold just topologically, and it has infinite fundamental group, and it has no surface subgroups at all. So what does that mean? So what's a group like that? Okay, so think of a surface group. You have a closed surface. Surfaces have this surfaces are sort of the very first 2-dimensional thing you'll encounter. Let me sound dumb, but just from an algebraic point of view, the surface group is sort of the first 2-dimensional group you encounter, in the following sense, that if you take any infinite index subgroup of a surface group, it's free. So if you pass to, just think of the finitely generated case, if you pass to a finitely generated subgroup that's of infinite index, well, how do I think of that? Well, I go to the corresponding covering space, and there's sort of some compact surface that carries the fundamental group, and it has boundary. Okay? And so the fundamental group of that compact piece is, is just a free group. It's just a surface with boundary. And then the rest of the surface is just sort of a bunch of annuli. So any infinite index subgroup of the surface group is free. So surface groups are sort of barely not free groups. So if you go any sort of depth in the surface group, you'll be free. So now suppose you had a 3-manifold group.
Can I stop you for a second? Do you happen to know whether there exist any other 2-dimensional groups with this property?
Yeah, so if you take, yeah, so I think if you take like a punctured torus and glue its boundary to like a meridian, I think that has the same property.
Okay. Okay.
I think there are examples, but I haven't checked though if that's an example, but I think there are examples. But at any rate, you know, we're all aware of this property for surface groups. So now imagine you have a closed three-manifold, and it has the property that it has no surface subgroups. Well, so now imagine a finitely generated subgroup of that three-manifold group, and pass to the cover corresponding to that subgroup. Well, again, there's some sort of Peter Scott proved there's some compact piece of that carries the fundamental group. And that compact piece will have boundary. And the boundary will be a surface. And either that surface is pi1 injective, in which case you win, you get a surface subgroup, or you can compress it. And so you compress it, and now you get some new surface. And maybe that is also not pi1 injective, so you just keep doing that. And either that terminates with some pi1 injective surface, or you can show that mild hypotheses that the three-manifold you started with, this compact piece is just a handle body, and so it has free fundamental group. So if there were a three-manifold with no pi1 injective surface in it, you would have a three-manifold group with the property that every infinite index subgroup that's, say, finitely generated was free. So it'd be sort of very strange group. It's like a three-dimensional thing, and every time you go very deep in to a very deep subgroup, it's free. So there's sort of no, I don't know. So psychologically, that's sort of bad for me. That would be very strange three-manifold. Okay. But anyway, we don't have to sort of worry about that. I just sort of think it's good to think about the hypothetical dangers of trying to prove this theorem. Okay. Right. Okay. So right, and then we need to promote this. So Kahn and Markovich give us this surface. So even if we assume we have some surface, we need to promote that surface to an embedding. The surface they construct is highly not embedded in M. And then a lot of this sort of, the Agel-Y stuff does a lot of sort of geometric group theory to do that. And so this is sort of where I'll sort of stop sort of contemplating the sort of hypothetical sort of counterexamples. But what I'd like to do is maybe, how Kahn and Markovich I mentioned is some very modern thing. But if you were being very naive, like I tend to be, how might you just try to find a surface subgroup without doing anything fancy? And you might try to just to use homology. So maybe a naive. So try to find surfaces more naively. So sort of try to use homology. Okay. So here's what I'd like to do is maybe I won't try to prove virtual Haken, I'll try to prove something much stronger. So that's always good advice, right? If you can't do something, just try to do something even more difficult. So say we have M down here, which I'll just draw as a blob. And then there are various things that could happen in the outcome of the virtual Haken conjecture. So I could have some finite cover here that has some pi1 injective surface S that's, say, separating. Okay? That's sort of the bare minimum of what the virtual Haken conjecture could say. So we could have some pi1 injective S. Okay? Or I could have something like this, where I have a pi1 injective S that's, say, non-separating. Okay? And maybe I'll use Dick Canary's notation for topology, is that you draw just sort of a squiggle somewhere to mean that there's interesting stuff going on in a schematic like this. So let me draw a squiggle in here to indicate that this isn't a bundle. So I don't want this to be an interval. And okay, so I could have sort of, the key point here is non-separating S. And then there's actually another famous conjecture due to Thurston that if you have a hyperbolic M, that if M is hyperbolic, and this is actually also a theorem, then there exists a cover M twiddle that's fibered. So this is the virtual fibration conjecture, which is also now a theorem due to Agel and Wise. And so this doesn't have any squiggle. This is actually a bundle over the circle. Okay. Okay. So this is. So these are sort of various refinements of the virtual Haken conjecture. This is sort of all you would know, is that there's just some pi1 injective surface that may or may not be separating. You could also ask the stronger versions, like, is there a non-separating pi1 injective surface? And then you could ask the very strong thing, is there a finite cover that's fibered? Okay. Assuming that M is hyperbolic. Okay, so the key point here is that this M twiddle has the property that, well, it has a non-separating surface in it, so H1 is non-zero. Okay, so in particular here, H1 of M twiddle, say with Q coefficients, is not zero. Okay. So in other words, H1 with integral coefficients has a Z factor. But I'll just write it quickly like that. Okay, so right. Okay, so right. Okay, so now we're faced. So if we have, and conversely, conversely to what I said and didn't write down, is that if there's an M twiddle with non-zero rational homology, then we get a surface. So then have pi1 injective surface in M twiddle. The idea is that the non-trivial class, the generator of the non-trivial class will be represented by a surface, and you can make sure that it's pi1 injective by a little topology. Okay. So this having a non-separating surface is actually the same as this statement. Okay. So now if we assume we're in this situation, how might we try to prove virtual Haken? Well, let's imagine that we have a counterexample. So we have a hyperbolic 3D manifold, and every finite cover has vanishing rational homology. Okay. So a nice thing about dimension 3 is that H1 of n with Q coefficients equal to 0 means that the homology of n for 3-manifold n, having vanishing rational homology means that the rational homology is actually the same as the homology of the sphere. So by duality. So so rationally this means you're just homologically the sphere. So if you had a counterexample to virtual Haken, or a counterexample to this, to virtual Haken, then you would have a closed hyperbolic manifold, and every finite index, every finite cover would be a rational homology sphere. Okay. So whether or not you find that unreasonable, I guess depends on metaphysics or something. Okay, so counterexample to virtual Haken. Give M such that every finite cover a Q homology sphere. Okay. Okay, so now what I want to do is I would just want to say, well, we know that if we assume that our 3-manifold is hyperbolic, then we know since its fundamental group is residually finite, we know there are lots of finite index subgroups. So there are lots of finite covers. So maybe there are geometric things that we can do using this wealth of finite index subgroups that would prohibit such a strange situation. So maybe there are just things I can do using algebra that make a finite index subgroup that's interesting enough that this is forced, to fail. Okay, so what can I do? Let's open our toolbox and see what we have that we can do with 3-manifolds and finite index subgroups. So what can we do in finite index subgroups? Okay, so again, M, I'm assuming is hyperbolic. Okay, and I also know, as a consequence of that pi1m is residually finite. So what can I do? I can make M, the thing I claim I can do is I can make M I can make the manifold very spacious by going to a finite index subgroup. So I can make such a manifold. Here I'm willing to change the topology by passing to finite index subgroups, so that's what I mean by make. So make such a manifold sort of spacious in finite covers. Okay, what do I mean? Well, I mean that I can make, if you give me any point, well, there's some amount of space around that point. It's called the amount of space you have is measured by what's called the injectivity radius. So the injectivity radius, if you have a point x, then I can embed some sort of hyperbolic ball of radius, say r, at x, okay? And I'll define the injectivity radius at x of m to just be the largest r, okay? So that this ball is embedded. Okay? that might not be exactly your definition, but there are a couple more or less equivalent definitions.
Oh, it's spelled that correctly.
That's pretty good. Some people do half of that or something. I don't know. Something. Okay. We just need some measure of how much space you have at a point. Okay. So how do I make this really big? Well, if this ball bumps into itself, I get a loop whose length is, say, less than 2r or something. So how do I get the injectivity radius big everywhere? In the cover. Okay. Well, just consider all closed geodesics of length less than any number, and then I'll just find a finite index subgroup that doesn't contain those elements, and I'll pass to that covering space. So what I can do is there are only finitely many closed geodesic loops of length less than, say, 2r, and I can make sure they don't lift. And to do that, I just use residual finiteness. So if you just give me one loop, and I can make sure it doesn't lift by just passing to any finite index subgroup that doesn't contain it. Okay. Okay. Is it an hour or an hour? Okay. That's good. Okay. So, right. So I can make sure that they don't lift using residual finiteness. So that means that I can find. So I have M twiddles as spacious as I want. So if you say I want a hyperbolic 3-manifold that has injectivity radius at least 100,000 at each point, then I can do that by just taking a cover of any given hyperbolic 3-manifold. Okay. So that's one thing I can do with finite index subgroups, and that's essentially the only thing I'm going to consider. Is there's other things you can do. But I can do that, and then I can ask, does that jibe with an example where this happens? So imagine you have this counterexample to virtually Haken, where every finite cover is a rational homology sphere, and now I know that I can make the injectivity radius large everywhere in a finite cover. So now I'm faced with this question: is that okay for rational homology spheres? So can I have rational homology spheres that are very spacious? And so this is a question due to Darrell Cooper. Are there rational homology spheres I'll just say they're arbitrarily spacious. So given what I've said out loud, that should be clear what I mean. Okay.
That sounds good.
Well, so it wasn't known when Daryl asked the question, and now it is known. So the answer is yes. So
And this answer comes from you?
no,
No.
no. So conditionally, so this answer of yes is due to Frank Caligari and Nathan Dunfield. So it's yes, sort of modulo the generalized Riemann hypothesis and parts of the Langland's conjecture, I think. And then unconditionally, shortly thereafter by Boston and Ellenberg. So Boston and Ellenberg just sort of saw what they were doing and then just explicitly constructed a sequence of hyperbolic manifolds using algebra. So you use words like p-adic, analytic, p-adic, completion and stuff like that. So I don't remember the argument as some. Okay, so these things do exist. Okay, which is either surprising or unsurprising, or maybe these two conditions seem unrelated. But just to think about it, like how would you just build a very spacious manifold from scratch? Well, you start with some huge ball, and then you try to glue it. You want to close it up into a closed manifold, and well, the manifold's sort of big everywhere. So if you glue it up, you can't sort of do it too close, or you make a short loop. So you sort of have to glue it in some interesting way. And if you can't sort of glue things together so that they're too close, maybe it's hard to sort of wrap things up. And maybe, I don't know, maybe you can create some homology when you do that. So like just directly attacking it seems complicated. So you want to try to wrap it up, but you may screw up the homology. So this is sort of interesting phenomenon. But let me mention that there are Q homology spheres, but I guess in these examples you can actually see that the torsion of the integral homology is going nuts. It's sort of really growing rapidly. So it's not like they are rational homology spheres, but the rational part is very important. So integrally, they're really far from being homology spheres. So we can ask the same question. So are there spacious integral homology spheres, where integral homology sphere is the same thing, you just replace the symbol Q with the symbol Z, and ask, are there spacious Z homology spheres? And this is unknown. Okay, so now there's a theorem due to Brock and Dunfield that they don't produce integral homology spheres that are spacious, but they're sort of mostly spacious. So there are most or pretty spacious, mostly spacious Z homology spheres. So what do I mean? Mostly spacious. I just mean that all the places where the injectivity radius is big, well, that part takes up most of the volume. Okay. So, so in other words, the set of points with a large injectivity radius takes up most of the volume. Okay. So in other words, for any r epsilon greater than 0, there exists a Z homology sphere such that the volume of the set of X so the homology sphere is called M. The volume of the set of X such that the injectivity radius at X is at least R compared to the total volume is at least 1 minus epsilon. Okay. And then let me just, because I'm low on time, let me just state. So then they asked, they have these examples, but then they asked, can you do the same thing using only, so the same, are there not integral homology spheres, but are there hyperbolic knots in the 3-sphere with the same inequality? So can you find knots in the 3-sphere so that the volume where the injectivity radius is big is almost 1? Okay. And so so with Jessica Purcell, we have this theorem. So there are knots, or mostly spacious knots. In S3. And so then what you can do is you can actually do 1/n surgeries on these knots, and you'll get new examples of integral homology spheres that have this inequality. Okay? And so I can briefly sort of say, sort of amazingly, sort of how you might go about doing this. And the funny thing is that even though you want to say something about a Z homology sphere, you start out with this kind of thing, where you have a fibered manifold. So what do I want to do is, how do I build homology spheres? Well, I could do something like take a Hegardt splitting of S3 and cut it open, and then like change the gluing map, but change the gluing map so that I don't change the homology, and then I get a whole list of manifolds. And then maybe I can do some geometry to sort of understand what's going on. So this gluing map, that's exactly sort of what Brock and Dunfield do, and they choose a gluing map by looking at bundles. So what do I do is, we saw earlier that if you give me any hyperbolic 3-manifold, I can pass some huge finite cover so that it's spacious. So if I start out with, say, a fibered manifold to begin with, like if my original manifold is already fibered, I can do that trick, and I'll get a cover where this is very spacious, and is as spacious as I like. Okay.
In that case, you don't even have to go as deep as Solberg's line.
Yeah, I can just go deep. Yeah, and I can do that, and the injectivity radius gets really big, and and it's still fibered because I can just pull back a fibration. So spacious and fibered. Okay, and then, okay, the genus of the fiber is now a lot bigger than it was to begin with, but S3 has lots of Hegardt splittings. Okay, so it has one in each genus. And so what I can do is I can sort of take a Hegardt splitting, and I'm almost done. Hegardt splitting. So this is just one thing I could do. Take a Hegardt splitting of S3, say, and cut it open. Okay, and sort of then maybe reglue. Okay, well up here I have some homeomorphism, say F, and I'll reglue with, say, I don't know, F to the N, okay, some high power of this, and I'll get some manifold that kind of looks like this, a cigar. And it turns out that using the sort of Thurston theory of sort of infinite volume 3 manifolds and the last sort of 35, 40 years of 3 manifold topology, the middle part of this starts to look like the infinite cyclic cover of our bundle. Okay. So as n gets big, you start to look like the infinite cyclic cover of this thing, which is also sort of spacious in the sense that the injectivity radius is big. So the middle part of this, so there's a very technical way it looks like this, and the middle part of this is very spacious. And what they prove is that the geometry at the ends is sort of stable as n grows. And so this part doesn't take up much of the volume, but all the volume is sort of in this very spacious part. So you can sort of do this thing where I'm talking about where you build a sort of very spacious thing, and then you try to tie things up without making a lot of volume. Okay? And then what Jessica and I do is, and so this sort of doesn't give you a homology sphere right away, but there are various tricks to make sure that F is sort of doing what you want. and you can actually control the homology arbitrarily. And then what Jessica and I do is...
You said they. Who's the they?
Brock and Dunfield,
okay.
Doing that. And then so what Jessica and I do is we come up with another sort of layer of tricks that allows you to do all of this while staying in S3 and making sure you have a non-complement. And so the picture there is that we'll have some sort of tangle in each handle body here. And then our mapping class in the middle will just be some very complicated sort of braid and then nothing is happening except for, winding these punctures around each other. And so that keeps you, the fact that you're not doing anything other than braiding the punctures means you're still in S3, and then you have to do a lot of geometry to make sure that the limit is still spacious and everything. But that's sort of that. So I'll stop there.
Questions?
So this is a hyperbolic knot complement you're constructing,
Mm-hmm.
so that the knot is not there.
Right.
Now, so there's a cusp there.
Right.
And of course, if you get out near the cusp, then spaciousness breaks down.
Right.
So, but somehow you're getting spaciousness away from the cusp.
That's right. So the cusp neighborhood itself doesn't take up much of the volume.
Yes.
And then another funny thing about knots in hyperbolic knots in S3 is they can't be literally spacious. So,
in other words, spacious except for the cusp.
Well, so even worse than that, I guess, is that You cannot construct knots in S3 that are like spacious just away from the cusp. So the shortest non-peripheral element in a hyperbolic knot complement is always like, has length like, less than 10 or something.
Okay.
So the cusp neighborhood in a knot complement in the 3-sphere always bumps into itself pretty quickly. So you can't literally make knot complements. So you could never produce answers to this, are there spacious integral homology spheres by using knot complements, because there'll always be at least one place where the knot sort of is close to itself.
I see.
So you should think about this, knot complements are like, they're very spacious most places, and way off in the distance you sort of see the cusp, like a rope, that's sort of, strung out through the 3 manifold, and it's sort of far away from you most places, and occasionally it has to come the rope comes close to itself. But for most of the manifold, it's really spread out. And there's some sort of place where it's sort of tied in a knot. And then the rest of the place, it's like, my wife's a knitter, so sometimes you take a skein of yarn and you put it on the winder, but it's like it doesn't come out and you have to untangle it by hand, because it's if you try to untangle it by hand, it's sort of mostly unknotted on your kitchen floor or something. And then there's one tiny spot where it's just sort of horrible. And so that's sort of what you think of these knots as being.
But does that mean that in that central section there, in that cylindrical section, you're not, the cusp is not bumping into itself? Or is that something you're proving?
Yeah, well, so it's like the cusp cross section in here, they're all very spread out.
Okay.
So that's another thing, is that in this sequence of manifolds, the genus and the number of punctures is going to infinity very fast.
I see. So you set that up ahead of time.
Right, because there's just some sort of cusp density argument. If the genus is bounded, you're sort of the cusps will have to get close to each other. So the genus has to be really big so that the cusp is spaced out.
So the bad parts where the knot is coming close to each other are being concentrated.
Yeah, they're sort of over here, yeah.
Any other questions?
It sounds like these examples, as you say, will be very high genus, many strands. Have you tried to find examples which, aren't such high genus and so many strands that you might actually be able to depict with SNAP-D or something like that?
Oh, no, yeah. No,
Okay.
yeah.
Is that hopeless?
I don't know. I mean, everything here is so inexplicit. I mean, so like you have to do this kind of thing to begin with.
Yeah.
And then we also can't get away with that immediately because we need a braid. So even if you start with a braid, you go to a 2-fold cover, it's like typically never a braid. It's not a braid anymore. So you go up here and this is like no longer a braid, so you have to do some trick.
Okay.
Yeah, and then, and then it's sort of, you need high powers, and so the knot sort of looks like a sweater in here. It's like if you drew a diagram of it. I mean, it just.
All right, let's thank Richard again.
Thank you.